All right, shifting gears slightly here, we're going to be talking now, moving forward the next few sections in regards to polygons, more specifically four-sided polygons. So polygons are plane figures. Basically what that means is they're closed figures. Think of all the shapes: triangles, rectangles, squares, trapezoids, parallelograms. Things that are not polygons are things that have hooked sides, things that crisscross each other. There shouldn't be any crisscrossing. And then things that are not closed. So those would be considered not polygons. So we name a polygon by starting at any vertex and then proceeding either clockwise or counterclockwise. You have the option. But wherever you start, you've got to be consistent. So you can't bounce around. So you're either going to go clockwise, so A, F, E, D, C, B, or you're going to go counterclockwise, A, B, C, D, E, F, either one. And in this case, you have to use the word polygon in front. A convex polygon is a polygon in which each interior angle has a measure that is less than 180 degrees. Those are predominantly the type that we're going to be dealing with. Polygon ABCDE is not convex because the angle that lies in the interior of the polygon at E has a measure that's greater than 180. So it's still a polygon, but that angle right here is going to be more than 180 degrees. It's practically a full circle if you look at it. All right, a diagonal is any segment that connects two non-consecutive, meaning not next to each other, non-adjacent vertices. So depending on the figure itself, that will allow you to figure out, all right, how many of these do I actually have? So you see a four-sided shape drawn here and then a five-sided shape, and you can see by the dotted lines all the different diagonals that are formed. But again, keep in mind, a dotted line will never connect two that are next to each other in terms of the angles of the figure. So what this section is going to go over, it's going to go over the vocabulary of all the four-sided polygons that we're going to talk about. So these are all special quadrilaterals, and then we're going to start to incorporate theorems with it afterwards. So the first polygon we're going to talk about are parallelograms. So by definition, a parallelogram is a quadrilateral, meaning four sides, in which both pairs of opposite sides are parallel. And I gave you a picture there with symbols on it. So both pairs of opposite sides are parallel. A rectangle is a parallelogram in which each angle is a right angle. So same picture, it's just now each of the angles is a right angle. A rhombus is a parallelogram. In this case, though, all the sides are congruent. So since it's a parallelogram, you know opposite sides are congruent to each other, but now we know all the sides are equal to each other. A kite is a quadrilateral in which two pairs of consecutive sides are congruent. So whether it looks like that, or it could potentially look like this, either left or right, up or down, either one, but you have two sets of sides that are consecutive. They need to be next to each other, and those are the ones that are congruent to each other. Then we have a square, which is a parallelogram that is both a rectangle and a rhombus. So what that means, a parallelogram, opposite sides are parallel. Rectangle, all the angles are right angles. And a rhombus, all the sides are congruent. So we're sort of pulling from each of the figures and combining it all into one shape. A trapezoid is a quadrilateral with exactly one pair of parallel sides. And the parallel sides are called the bases, because a lot of times that's what it sits on, but there's only one pair of parallel sides. For an isosceles trapezoid, that's a trapezoid, follows the same definition as 6 did, but now it gets a little bit more specific. It's a trapezoid in which the non-parallel sides, they're called the legs, are congruent to each other. And then a little bit more vocabulary that goes along. So this is a leg, and this is a leg. And then you have your upper base angles and you have your lower base angles. The bottom ones are the lower base angles, the upper ones are the upper base angles. So let's just do one practice one for right now here. So it says we're going to prove that in a parallelogram, each pair of opposite sides are congruent. So we're going to prove that. So we're given a parallelogram or a diagram. That's our given. Now, the diagram originally just looked like this. So A, B, C, and D. Now, what would be helpful, and what I wrote in 2, is you're going to draw an AC. So that's where that extra line comes from. And what I would do is, instead of construction, I would write 2 points, determine a line. Okay, so 2 points, determine a line. Anytime you draw in a line, that's the reasoning. Then we know AC is congruent to itself by the reflexive property. If this is a parallelogram, then we know that the opposite sides, by definition, so you don't need to say it, if you know it's a parallelogram, then the definition holds. But we know that the opposite sides are parallel to each other. So if we have now just drawn an AC, which is your transversal, we can now go over different types of angle pairings. So what we can say is that, if I swap colors here, we know that BAC and DCA are congruent. And I'm going to add one thing here that says parallel lines implies alternate interior angles congruent. And then the other pair is this pair right here, because we have 2 sets of parallel lines. So both sets of alternate interior angles are congruent to each other. So both the bottom triangle and the top triangle are now congruent. We have 2 angles and we have AC in the middle. So they're both congruent by angle side angle. Therefore, by CPCTC, we can say that AD is congruent to CB. Order is very important here, so be careful. Don't just label them because they're going in the same direction. If you're going from A to D, that means